All right, let's continue. So what the picture here, just to complete the argument, is something, let me just keep that. So what is happening here is actually we have these cyclotron orbits in the inside the sample, and they're like, I think depending on the magnetic field, let's say they are like that. But when you come to the sample edge, what they are going to do is like they are going to do this skipping, so-called skipping orbits. Yes, like, so they are generally drawn like this. This one is up and this one is down, but what is happening is actually like this. Let me attempt to draw something like that. These are semi-classically, right? Kind of like they want to do the circle, but because of the strong potential and at the boundary, they reflect and they try again and they try again and they try again. So these are what we call skipping orbits. And the question is, if I have like a impurity at the boundary, let's say I have like an impurity at the boundary. In the Landauer formula, if you remember, we just said there's like a transmission coefficient, and that's it. There's no difference. And am I supposed to do exactly the same thing here? So let me write that. In Landauer, G was equal to E squared over H times T in case of impurities. Here T is transmission coefficient. So are we supposed to do exactly the same thing here? So the answer is no. Here, if you want, in integer quantum Hall H, T is equal to exactly 1. And the reason for this is like, suppose there is like a current here, right? There is like an electron, and the electron is going like this, and it's like going an impurity, and it wants to scatter back. When it's when it back scatters, it needs to go in the opposite direction. But this is not like, right, you need a quantum state to be able to do that, right? If there is no available state, you cannot do that. And the back scattering channel is on the opposite side. And there's like a wave function here, if you want, there's like a wave function. Because they are like macroscopically separated, the overlap of wave function is like negligible. So this electron going there, even if it wants to scatter, it cannot scatter, because there's nothing it can do. So it has to just keep going in one direction. That's why we call that chiral edge modes, because there's only one way for going, which is like in the present case, it is like counterclockwise, right? Because of the magnetic field we choose. And this guy can go up, this guy can go down. So this argument, so even if like we have like, so what we want to consider is like a strong magnetic field where L is smaller than all other scales, like impurity scale. Then we can consider like the now I'm like slowly turning on impurities, even if like suppose we have not this, right? Rather than that, suppose we have something like that. I don't know, some jagged landscape, and all the levels are going to be occupied here up to whatever is given, and here is Fermi level on one side, Fermi level on the other side. As long as my Fermi level does not reach to this fluctuation in the impurity scale, they are not going to matter, because for every state that's going up, there is a state going down here. For every state going up here, there's a state going down there. So the bulk by itself doesn't matter, only the edges matter, and edges are going to give you this integer quantum Hall plateau. Now we are ready to consider a little bit of the difficult problem. I want to discuss semi-classical percolation, and so the key observation that we are trying to understand is these quantum Hall plateaus. So there is like an extended region in this is like sigma xy, and they transition like this to another plateau, something like that. There is like a finite region. So this is sigma xy, and during this transition, inside here, sigma xx is 0, like that. But whenever you come to these like transition regions, it just picks up like that. And here it also peaks, maybe a little bit in the transition region. And this, the center is like some magnetic field, but the question that we want to understand is like there's like an extended region of magnetic field that this plateau exists. Okay, plateau persists for some b goes to b plus delta b. That's the one we want to understand. So now we are going to consider this order, but this order, if you just exaggerate, it's just going to wash out all the effects. We are thinking about this in the integer quantum Hall effect, even more so in the fractional quantum Hall effect. We are considering smooth weak disorder. What this means is like the energy scale coming from this order should be much smaller than lambda level spacing. So this order is not like no lambda level mixing. And in the scale of this order, these cyclotron orbits are smooth, exactly like in the edges. So what this means is like we are saying, yeah, we are considering this order, but it is still a clean system. So there is like a very subtle effect that we are trying to understand. It is essential, but it doesn't mean we have like impure samples. Now let's try to remember what we did. So first, I want to start talking about density of states. So this is d of epsilon. So this is epsilon. Suppose this is b is equal to 0, and this order is also 0. And what we found was something like that. Right? Like we are in two-dimensional system, and density of states is constant. And we later turned on magnetic field, and this blue line turned into these single Dirac peaks, like Dirac deltas. And the separation here was h bar. If you want, this is like h bar omega over 2. This is 3 h bar omega over 2. And this is 5 h bar omega over 2. So this is B non-zero, but this order is still 0. And lastly, I want to consider what happens if you turn on this order. If you turn on this order, what is going to happen is like these single Dirac delta functions, they are going to just broaden. Right? Something like that. And the scale of broadening is like something like h bar over tau. Tau is the elastic scattering time, and the smooth impurity or like weak disorder means we still need to have h bar over tau much smaller than lambda level spacing. So this separation between these two peaks is much bigger than the width of a given peak. And now let's remember what happened in the presence of H. So in the presence of H, so suppose this is our H, and what we had was like these skipping orbits, something like that. Let me put it arrow like that. And now I want to consider like deforming this boundary. So this is the wall, which is kind of like an infinite impurity if you want. Now I want to think about deforming this wall, right? And what is going to happen is like these skipping orbits are also going to deform. Like these are semiclassical orbits. If you want, the electron is going to go and find equipotential lines, and it's going to do this, its thing along this equipotential line. Then it is not hard to imagine. So if we have like, suppose like a container like this, so our electron is just going to go there, and it's going to do its like chiral circulation, which is like this, but let me not write that. So now we can imagine this to be not infinite but finite. So from the top, so this is from side view, suppose I have something like this, like a bump, and around this bump I'm going to have these circulations. And if I look at it from the top, there is like I need to think about these like contour maps, and around this, like they're like, I don't know, they're like some equipotential lines, and then my electron is going to find some energy matching its own energy, and it's going to do this circulation. But we can also do exactly the same thing. It could be like, so this is a hill. We can also think about a valley like this. Suppose there's like a valley here. In this case, electron is going to do not this, it's just going to reverse its direction, right? So typically, in the previous case it was like that. In this case, it's going to just reverse it. And the way we show this from the top is like, there's like a minus in the center, and there are like equipotentials, like a contour map. And electron is just going to find equipotential line, and it's going to do, it's like, okay, this is going to be a reverse direction, like that. Then in the case of a 2D sample, let's think about a 2D sample like this. And now I can think about like my Fermi energy. So okay, let me just write that. Rather than tuning B, we can fix B and tune Fermi level, which is going to be the same thing, because what is going to happen is like, as you increase B, you are going to increase the separation of lambda levels, and occupation of lambda levels are going to increase. But if you fix B, there will be like a fixed occupation, and if you change the density, right, you are just occupying the same lambda level with more states. It's going to be exactly the same thing. But this picture is a little bit easier to think about. So if my Fermi level is smaller than a given n plus a half, what I need to have is, I have these little lakes like this, maybe another one here like that, another one here like that, and that means, and of course in the edges we also have like a picture of edges. In the edges I have like a current on that direction like that, and there's like a current on this direction. So in this case, Ix is 0. What this means is like sigma xx is 0, and here sigma xy is going to be e squared over h for one state. Now I increase E Fermi to match to this lambda level. So what happens is, okay, suppose I do it the other way. Suppose I go above the lambda level, because let's consider E Fermi bigger than lambda level. In this case, we have exactly the same thing, but these, rather than thinking about lakes, I need to think about dry land, right? All landscape is going to be filled with water. Only a few like patches of dry land will be remaining. So let me draw it like this. I don't know. So there's like something here, something there, something here, and the entire landscape is filled. If you want, there is like in this case, lakes of little holes remains. In this case, lakes of little electrons remain. In either case, Ix is 0, sigma xx is 0, sigma xy is e squared over h. But right in between, if you consider the middle between these two, there must be a point where these lakes start to so-called percolate. So what this means is like the typical size of these lakes are going to be large, right? Suppose there is like a landscape and you slowly increase the water levels, and at some point flooding starts happening, right? You can just, if you are in a boat, you can go from any point to any point because lake connects you anywhere to anywhere. And when this happens, like, okay, maybe something like that, and maybe something on the edges, maybe another lake here, and an electron here is going to be able to go through water without any interruption. In that case, Ix is going to be non-zero, sigma xx is going to be non-zero, and sigma xy is going to be different from e squared over h, because all of these arguments we laid out are going to be invalid. And here, this is what we call percolation threshold. Okay, this is a little bit dirty, but I think very compelling argument. Let me try to clean up the argument by just laying out what is actually happening. So let's go back to experiment. So what is happening is we have, let me start from one plateau, transition to another. Let me try to do it like this. Okay, one plateau, transition to another plateau, and then transition again. Okay, I cannot draw. Let me draw it like this. So this is sigma xy, and if you increase system size, what happens is something like that. So there is like a critical point here, they intersect, and here something like that. So this dashed line, so this one is small t or small l. This dashed line is okay, this is not small t, this is big T or small l, and the dashed line is smaller temperature or bigger sample. So as the sample gets bigger, these transition lines from one plateau to another one becomes sharper and sharper, and they intersect at these critical points. So this is one observation. For sigma xx, what happens is So let me try to align these points, something like that. For sigma xx, I have this solid line. Okay, good. So what happens here is like as I inside the plateau, this this sigma xx is going to be 0, but as I approach the transition points, it's going to peak up. That's at least what we see in the experiments, the observations. And if you make the sample bigger or temperature lower, what you are going to see is like these things, they are going to get bigger. Something like that. So these are the percolation transition points. And what this is telling us is like transition is getting sharper and sharper as you go to lower temperature or bigger system sizes. Now we have to remember all these things we mentioned in the localization. So in the localization theory says in 2D all states are localized indiscriminately, right? That's what we said in the previous chapter. But there are like a couple of differences in the present problem. First, here there is like a magnetic field which says broken time reversal symmetry. Right? So then states cannot be, at least these weak localization arguments we laid out cannot be applied. What we are seeing is sigma xx is non-zero around plateau transition. So what this is saying us is like actually this localization theory we laid out, it seems to be not working because of that, right? Because sigma xx is peaking up. And also the sharpening of steps suggests like a kind of phase transition of steps suggest a phase transition, which is this so-called percolation transition. And in the case of a phase transition, we know that there is like a correlation length, like correlation or localization length, localization length. Psi is a function of either temperature or psi is a function of system size. We can consider either one of those, and it or we can combine these two, and psi we can think about it as a function of energy. This is going to be blowing up as energy approaches one of these h bar omega n plus half. So as energy approaches right between the two harmonic oscillator levels, this is going to blow up. Okay, let me just say these results, and there's like one very nice argument I want to finish there, but what Halperin suggested is like Halperin 1982. He said so this is, let's think about only one lambda level, and so this is density of states, so this is energy, and this point is some h bar omega n plus a half. And Halperin suggested that all states are localized except one in the middle of this lambda level, right? So this one is delocalized. So all these blue regions, they are localized. And suppose this is my Fermi level, this green line. And what is happening is, like, if my Fermi level is in the localized regions, that's an insulator, and that means sigma xx is 0, right? And sigma xy, which is what we calculated, is quantized. And as I go and go, it doesn't change, right? Because I'm still in the insulating region. It doesn't matter what my Fermi level is. They are still localized. But as soon as I hit this single delocalized state, my sigma xx is going to be non-zero. Right? Now there will be a percolation transition, and there will be conduction from one edge of the sample to the other. But if I pass through that, sigma xx is going to be 0 again, and sigma xy is going to be quantized, and it is going to continue until you hit the second lambda level. And by symmetry, right, by symmetry of this argument, because there's always another lambda to the right and to the left, the transition needs to be in between these two lambda levels. Okay, there is one last argument. So this argument is a little bit simpler. This is due to Laughlin. Sometimes people call this Laughlin-Halperin contraction, and I'll finish after that. This is 1981. So Halperin suggested in 1982, but by the time he suggested this, he already knew about Laughlin's paper. And so Laughlin considered, so rather than this whole bar, he considered, like, right, there's like these are periodic boundaries. He said, let's consider this disk, something like that. It's harder to draw. So this is yes, 2D, but like we said, like we have like periodic boundaries in y direction, so we connected to the like this cylinder geometry. So this is still Lx, and this circumference here is Ly, and he also suggested on top of this, let's put like a flux through this tube. So this is flux. So there are two kinds of fluxes. One is magnetic field, right? Magnetic field perpendicular to the electron plane, which is going to be like emanating from this, right? On the top of this, Laughlin considered another flux going through the cylinder. This cylinder is going to change the boundary conditions. If you remember, we had e to the I kx should be equal to e to the I kx plus L. In this case, there needs to be like an additional shift due to this phi, and you can have, for example, here plus or minus depending on the flux, and you can even have e to the I phi, right? This is like Aharonov-Bohm effect. That's going to affect how much flux you trap as you go around the ring. So let me write that. So this A is equal to 0 minus Bx 0. This is perpendicular B field. On top of this, we also have like additional A, which is going to be 0 phi over Ly 0. This is flux in cylinder. And now we are considering changing this flux adiabatically. Suppose this flux is time dependent, right? And if the flux is changing, we know Lenz's law, right? There's like a Faraday's law. If you change the flux inside the metal, right, you are going to generate an electromotive force around the perimeter. Right? That's the nice thing about this argument. All of these advanced things you don't need to consider. This is like almost like a freshman calculation. So phi of t increase flux. That means there is going to be an electromotive force around the ring. And that one is going to be Vy is equal to minus 1 over C del phi del T. Change of flux is equal to electromotive force. Or electric field Ey is going to be minus 1 over C del Ay del T. This is exactly the rewrite of the same thing, and this is going to be minus 1 over Ly C del phi del T. And I am interested in Hall current. Hall current is the current perpendicular to the electric field. In this geometry, electric field is around the perimeter, and Hall current is going to be along the axis of the ring. So let's write that. So J, in this case, J is going to be along X, sigma xy, and Ey.
Along X?
Yes, we changed it. That's a little bit unfortunate, but previously we were running voltage along X direction, and Hall voltage was along the perimeter. In this case, in Laughlin geometry, we are applying the voltage around the perimeter through the flux, but because Hall voltage is going to be perpendicular, we are looking at like Jx on that direction. And suppose we increase flux by some delta phi, and I can consider change in rho, which is going to be dt jx, right? I'm just integrating current to get change in charge density, and this is going to be I'm just writing this now, sigma xy dt Ey.
This is continuity, isn't it?
Yes, this is the I wrote the continuity equation.
But there is a dial J to J or dial J?
This is not the continuity. This is like J is delta rho delta T, right? Right. Current is minus E times current is I is equal to Q over T, right? Charge divided by time. Di is equal to dq over, and I just integrated both sides. I think this is not even right. If you want, this is kind of like a dimension, right? It's not even continuity equation. Even simpler than that. You don't even need to know that. So this thing is going to be minus sigma xy. Now I am like plugging in this thing I just have here for Ey. 1 over Ly C dt del phi del T, and this is going to be equal to minus sigma xy 1 over Ly times C times delta phi. So this Ly I can absorb. So this Ly, okay, so the ring is something like this. So this is the Hall voltage. This is Jx, And if I multiply Jx with Ly, this is going to be delta Q, right, is equal to dt times Ix. I just took this Iy and multiplied Jy, right? And Jx times Ly is going to be total current along the cylinder, and this is going to be, I just rewrite this sigma xy 1 over c delta phi. Okay. And now is the argument. So I want to change flux from 0 to 1 flux quantum, which is going to be hc over E. And in this case, if delta Q is equal to minus E, that means if we are transferring one electron from left edge to right edge, let's write this and see what this gives us. Minus E is equal to minus sigma xy 1 over c hc over E. Okay, c's cancel. Okay, minus are going to cancel, and sigma xy is going to be E squared over h. Okay. And this argument is valid regardless of disorder and whatever happens in the boundary or the impurities at the edges, all of these regardless of impurities, because we just use like a basic law of physics, and that explains why we had this sigma xy quantization. Basically, like it's just coming from gauge invariance and like this flux insertion and this Aharonov-Bohm effect. Maybe I can stop here, not to go too much. And any questions or comments? This is a little bit, I know, too much, but I think arguments, this is, if you want a little bit like general knowledge, like there are like many arguments laid out. You may or may not remember them, but that's how people think about this problem.